Hey everyone, it's Mr. Anderson back with you one more time. Today we're getting together to talk about section 7.1.2 from our Common Core Algebra CPM ebook. And our goal today is to talk about the connection between an exponential graph and a table of a graph, or the equation and a graph, or a situation and the table, right? We're going to use our framework that we developed earlier this course right here, using this little connections web that we've got over on the right hand side of our ebook there. And we're going to talk today about some of those things and how we can facilitate some of those things. I put together a couple notes. I'm going to go back and forth between the book and my notes and a Desmos tab for our opportunities today. And we've got a problem that's really going to allow us to get started pretty gosh darn nicely. It says in 720 from section 7.1.2, it says, let's look at some of the connections between multiple representations and an exponential function. So I'm going to take that and I'm just going to run with it. We are dealing with an exponential function. We remember the ball drop example or activity from earlier in the course. And we've got a graph and we've got a table, and we're asked about this thing called a rebound ratio. Now, if you don't recall, a rebound ratio is when we drop a ball from a fixed height, how high back up, or to, what proportion of the drop height do we expect it to bounce back up? Okay, and what we're asked is, at what height did he drop the ball? Now, for me, that screams, okay, we want to figure this out. Well, we know it's exponential. We know we're dealing with a rebound ratio, so we can use a common ratio to make some of these calculations. I've got the second, third, and fourth bounce here captured, and we're going to go ahead and we're going to model it, and we're going to write an equation, but I've got to work all the way backwards. In order to do that, I've got to figure out what that thing that goes in green there. And I'm going to utilize Desmos a little bit here because Desmos does have a calculator. Remember, the rebound ratio can be found by taking a bounce height and dividing it by the previous bounce height, right? We're going to get back a fixed percentage if we remember that learning from earlier. And if I just go to Desmos.com and I click on the graphing calculator, I can actually do this math here just by typing into these slots and I made a mistake there. I got one too many decimal points down here. And it'll give me that 0.8, that 80%. And I'll check the next one. The next one was 54.1, and I'm dividing it by the previous one, the 67.6, and it should be 80%. Now, it's not exactly, and that's likely because there's some rounding going on. And that means that my rebound ratio is 80%. And I'm just going to make a little note there. My rebound ratio is 80% or 0.8. And that matters because whatever number went here, I took and I multiplied it by 80% to get that. Well, so I can just work backwards and do the division, right? I can go like this. I can say, okay, well, what's 84.5 divided by 0.8? And that's got to be the 105.625. That's what goes right here. 105.625. And I can do the exact same thing. Let me see, I'll take that value, the 105.625, and I'll do one more division, divided by 0.8, and that gives me the 132. I'm going to just call that, I know I'm rounding, and I'm taking some liberty with that rounding and creating some error, but I'm going to call that 132 for our purposes. And again, there's some round off error that I'm going to be creating, but that's going to be my starting height. And why do we care about the starting height and the rebound ratio? Well, because folks, those are the two things that we need to write that equation. Remember, we've got this general exponential form, y equals a times b to the x power, okay? And what we're going to do is we're going to take this and we're going to use that drop height, that starting value, that height that we have with 0 bounces. That's my 132. And I'll multiply that by my 0.8 to the x power. And what I'm going to do, or going to be able to do, is I'll be able to graph that, and I'll be able to see if that fits in the, and passes through those lines here. We'll check that out in just a second, okay? Let me just let me steal. I want to do this from that. So I can just scroll down here and I've got that thing graphed. And one more time, I can just go to Desmos. I'll clear these things out because I don't need them. I'll add just very quickly a table. And actually, you know, might be time. We got time. I can do this quickly. 132, 1, and 105.65, and 2, and 84.5, and 3, and 67.6, and 4, and 54.1. Okay, so now what I'll do is I'll make sure I can zoom out and I can see those. And sure enough, there's my graph, and it might be helpful here for me to just do some quick adjusting. Why don't I just quickly change this from like -1 to 5. I'm sorry, I got to do that on the x-axis. Oops. -1 to 5-ish or so, and voila, I can see that. And now what I want to do, and I see some slight curvature there, but now what I want to do is I want to graph my function that I think is going to be pretty gosh darn close. Y equals 132 times 0.8 to the x power. And holy cow, look at how nicely that, maybe you can't see that because it's blue or purple. Let me see, turn that back on. Should make that red, and now we can kind of see those. I'll turn the projector mode on. There we go. And now we can see how nicely that fits through those points. And now we would be able to use that as a predictive model. Okay, I'm going to keep on here. In our notes, a major tech company, Expo Grow, is growing incredibly fast. The last prospectus, which is a report on the company and its growth and profits and dividends, etc., said that so far the number of employees Y could be found with the equation Y equals 3 times 4 to the x power, where x represents the number of years since the company was founded. How many people founded the founded the company? How can the growth of this company be described? Well, if I take this and I write it just like they give it to me, Y equals 3 times 4 to the x power. Remember, this is our starting value. And what that's representing is the number of people who started the company. So if I was going to say, hey, how many people started the company? I'd say 3. And then how can this growth be described? Well, this is a multiplier, right? This is our growth multiplier. And we're multiplying by 4 every single time. That's what that exponent represents, that 4 repeated multiplication by 4. So we have a word for this. Quadrupling. And that just means multiplying by 4 or growing 4-fold, or something like that. Okay? And that's just also another exponential function. Okay? Another exponential growth function. The first one was decay, this one's growth. All right. A virus, computer virus, is affecting the tech center in such a way that each day a certain portion of the virus-free computers is infected. The number of virus-free computers is recorded in the table at the right. How many computers are in the tech center? What portion of virus-free computers is infected each day? How many computers will remain virus-free at the end of the 3rd day? All right, so what I'm going to do, so I'm just going to go ahead and continue this table. Maybe I'll even do this. But I want to put a 3 in there. I want to figure out how many viruses are gonna be there, uninfected computers. Sorry, and first thing I want to do is recall that when x is 0, this right here is going to be my start value. So how many computers are in the tech center? I'm going to go ahead and say 27, right? Because there's my start value. Now I got to figure out that ratio from here to here again. And that same ratio should take me from there to there. And I'll check this one more time using Desmos. Desmos is going to be a pretty nice tool for this. I'm just getting rid of those things. No big deal. I can take 18 and divide it by 27. Oh, and that's 2/3. Okay, I'll check this. Is 12 divided by 18 the same thing? And it sure is. So 2/3, or 0.6 repeating, is going to be my decay factor in this case. And so what I can do is I can just take 12 and I can multiply that by 2/3, and that should tell me at the end of the 3rd day how many computers remain uninfected, and that's going to be 8. All right, and I have that. I just threw that down in our notes there. And we can justify that by continuing the pattern, right? We can say our b in this case is going to be 2/3. And if I wanted to write my equation, I could do so like that. And I could plug in a 3 for that x, and it should give me a value for y. Okay, as part of a major scandal, it was discovered that several statements in the prospectus for Expert and Part B were false. The company actually had 5 founders, and it doubles in size each year. Okay, what equation should it have printed in the report? Well, the base equation is not, or I'm sorry, the parent equation in this case is not going to change. Y equals a times b to the x, right? A is, of course, going to be that start value. B is going to be our repeated base of multiplication. This right here is going to be our 5 founders. We're starting with 5. And that is going to be doubling every single year. And that's noticeably different. You start with 5 and you double it, you get 10. So that's going to be bigger, right away. But gosh, not after the first year, right? Because you start with 3 and you quadruple, you got 12. So pretty significant is that growth, right? Okay, let's move on to one more thing. And then we're going to talk about a little bit of review preview. We're going to talk about how we created some connections, and we're going to be done. Okay, most of the exponential equations you've used in this chapter have been in the form y equals ab to the x. In fact, that's what we just did. Explore this using the E tool. Click in the lower right-hand corner to view it in full screen. What does A represent in this equation? What does B represent? Well, we already, identified that represented, starting value and growth rate. But check this out, because graphically, they're slightly different. And I'm going to use the E tool for this. And I can do so, right? If I just click on play for A, look what's happening. As A gets bigger, what's changing? I think you guys see it, that y-intercept is changing, right? Check this out. If I just take this, right here, and this is going to be some future learning that's coming up here. When A is 3, that's where my y-intercept is, and I can verify that there. Now, likewise, I can do this, make it 4. Okay, so is this going to be 4? Sure is, right? So A is not just the start value, but it is the y-intercept. Well, how about B? What does B represent? Let's goof around there. Right, B. Yeah, B is still that growth factor, right? There's B's negative, okay. But look at when B gets bigger. Look at how much steeper that line gets. Holy cow. So A is that y-intercept. B is still that growth factor. How can you identify A by looking at the table? Well, we already kind of gave this away. Look for when x is 0. And conveniently, that's true in our linear functions as well. When x is 0, that's where our y-intercept occurs, right? That's a good idea, right? How can you find it in a situation? Well, we're going to look for words like starting value or started with or something like that. All right? And then how can you determine, I'm looking at part C now, how can you determine B in each representation? This is just going to be that growth factor or that multiplier. Okay, you guys can definitely identify that with words like 2 times, 3 times, twice, doubling, etc., etc. We definitely spent a lot of time today connecting the table and the equation, but we also connected both of those things to the graph. And if you think all the way back to the first problem we did, we connected them both, all 3, to the situation. So we've got a lot going on here in terms of some of the connections, and I know I went quick with some of these items today, but ladies and gentlemen, the goal was to give you an opportunity to, try some of these things, pause, reflect on some of these things, and then move forward with a little bit of knowledge on some review preview questions. Speaking of review preview, we've got a couple here. We're going to look at 24, 26, and 27, just 3 of them today. And these are some problems that if you're trying them, they're really going to kind of give you the feedback that says, hey, I got this, or, I've got to ask some questions about some of these things. So we're going to ask you to try them. It's going to give you an idea of what kind of questions you should ask. And, it's up to you to follow through and ask those questions. Ladies and gentlemen, thanks for watching. Have a great day.